Hey, it's Noam, and we have a special episode this week. Unexplainable recently got a cool opportunity to make an hour-long radio special to air on radio stations across the country. To make the radio special, we took our first ever episode, the story of Vera Rubin and her research on dark matter, and we coupled it with another favorite episode of ours. It's about how a 2021 experiment on a certain subatomic particle called a muon might offer scientists a new clue in their ongoing search for dark matter. But we didn't just want this episode to live on the radio. We wanted to bring it to you, our podcast listeners, too. So, here it is. I remember the first time I saw the movie Men in Black. I must have been in like 3rd or 4th grade, and the whole thing was pretty fun. It was breezy, action-packed. And then I got to the final scene. The camera zooms out. You see trees, all in New York City, the Earth, the moon, Saturn, entire galaxies, until it zooms out so far that you can see that everything is just inside a tiny marble. And there's a whole bunch of other marbles in a bag. And these aliens are just tossing them around. It kind of terrified me. I had these nightmares about being stuck in that bag of marbles, just thinking that everything I knew and everyone I loved was so small. Even our universe was insignificant. But that was just a movie. This is a story about the scientist who discovered it was real. Not the aliens part, to be clear, but she discovered that everything we can see, everything we can touch, everything we know is just a tiny sliver of what the universe really is.
So it's the late 1960s. It's evening time. The stars are coming out. Just outside of Tucson, Arizona, out in the desert at what's called Kitt Peak National Observatory.
Science writer Ashley Yeager.
Vera Rubin, an astronomer who's very interested in how galaxies work, and Kent Ford, her collaborator, are getting ready to point one of the telescopes at Kitt Peak to the night sky.
They've got this new cutting-edge telescope, and they're pointing it towards stars at the edge of a spiral galaxy called Andromeda.
And they're trying to get the speeds of these stars. How fast are these stars going around Andromeda?
Up until that point, there was an assumption about how stars in other galaxies would move.
That the stars closer in would fly around the center of the galaxy, and the stars farther out would go slower than the stars closer in.
The idea was that they would basically work like planets in our solar system.
So Mercury is flying around the sun because it's so close in.
It's going super fast, more than 100,000 miles per hour.
You know, it's getting all of that gravity from the sun. Pluto's super far out.
Getting less gravity from the sun, going like 10 times slower.
So it's kind of just like, I'll get there someday.
But this idea that stars further out would go slower like Pluto, it was just an assumption.
Almost no one had attempted to do things far out in a galaxy.
Vera passed away in 2016, but we've got recordings of her old interviews.
And I was always skeptical in the sense that I thought if you hadn't learned something, you just didn't know it. You couldn't just infer it.
And Vera was after something big.
I guess I wanted to confirm Newton's laws.
So they're out there at the telescope, slowly gathering data, and as they do, Vera notices something unexpected.
We found that the stars very far out were going almost exactly as fast as the stars in the interior.
These stars, these hot young stars in Andromeda, are moving way too fast than what Newton's gravity would allow for.
They're going so fast that you'd expect them to just fly off, slingshotting into space.
It was just so different than what everyone had expected.
There were two equally unsettling explanations.
Either Newton's law of gravity is wrong, or we have no clue what's going on at the outer edges of a galaxy. There's got to be something happening out there that we don't understand.
This is Unexplainable, a show about all the things we don't know. I'm Noam Hassenfeld. This isn't a show about answers. It's about the questions. why they matter, what's standing in the way of a solution, and how to grapple with the unknown. We're starting with one of the biggest scientific unknowns. What is the universe made of? That observation Vera had out there in the Arizona desert, it set her on a path to confronting this massive scientific question. And it would ultimately upend what physicists thought they knew about the universe. But it's not like Vera had a eureka moment on the spot.
I mean, in retrospect, I was terribly stupid because I didn't get excited about it.
When she made her observation, Vera had a few options. Option one, she could dismiss it, just like say it's not a big deal.
I mean, when you first see it, I think you're afraid of making a dumb mistake. You know, that there's just some simple explanation.
Option two, she could do something that happens often in science. Come out with a grand, sweeping conclusion based on limited data.
And of course, in science, it can be a bit of a race.
But Ashley Yeager, the science writer, says Vera went for option three.
She wanted to collect more data. She never assumed anything. She was always like, okay, well, I don't want to just believe that. What's the data to support that evidence?
Honestly, this is one of the things that makes me admire Vera so much. She had this chance to wow the scientific world with some bonkers conclusions, and she waited. She was careful.
And so Vera and a couple other people, they really start to do a systematic study of galaxies.
And it wasn't just a one-off in Andromeda.
They all show this bizarre behavior of stars, these stars out far in the galaxy moving way, way too fast.
The data pointed towards an enormous problem. The stars couldn't just be moving that fast on their own. They needed some kind of extra gravity out there acting like an engine. And there had to be a source for all that extra gravity, which would mean
there's got to be a lot of mass out there that is tugging those stars along.
Except even when scientists looked through the most advanced telescopes, no one could see any of it.
That raises the next question of, what is it?
Vera and other astronomers could only guess.
Maybe it's black holes and, really faint stars and planets that we can't see. They would say that it was baseballs. They were teasing, obviously. But as they're looking out there, they just can't seem to find any kind of evidence that it's some normal type of matter.
At a certain point, they basically have to say,
we really have no clue what it is.
And this is where it all gets way weirder.
There's this invisible mass, what astronomers call dark matter.
Dark matter.
Hanging out at the edge of these galaxies, tugging those stars along, making them move super, super fast, way faster than we would ever have assumed.
To move this many stars, there would need to be a staggering amount of dark matter, more than all the rest of the normal matter in the universe combined. But it was completely invisible, which naturally raised a lot of questions.
What is this stuff?
No idea.
Is it the stuff that makes up you and me? Is it normal matter?
What does that even mean?
Or is it something completely different that we have to kind of rethink our entire structure of the universe?
That's what it was starting to look like, which is probably why in the 60s, the idea wasn't exactly catching on. Decades before Vera, other scientists had seen stars and galaxies moving too fast. And they'd had the same three options Vera had out there in the desert. Some chose option one. They dismissed it. Some went for option two. They made sweeping conclusions about dark matter, but they didn't have all the data that Vera had, so the idea of dark matter just kind of floated at the fringes of science for decades. I mean, it takes a lot to make scientists rethink the entire structure of the universe.
I think many people initially wished that you didn't need dark matter. It was not a concept that people embraced enthusiastically.
And then came Vera and all of Vera's data to really turn things around for dark matter.
She does 20 galaxies and then 40 and then 60, and they all show this bizarre behavior of stars out far in the galaxy moving way, way too fast.
I mean, it just piled up too fast. Observations were undeniable enough so that most people just unenthusiastically adopted.
So at that point, the astronomy community is like, okay, we have to deal with this.
Vera convinced the world where previous scientists couldn't.
And I think it's because she did this in so many galaxies. We're talking 60 galaxies. There was really no denying it.
Ultimately, in a 1985 talk to the largest body of astronomers in the world, almost 2 decades after that moment in the Arizona desert, Vera had enough data to declare her grand, sweeping conclusion. Nature has played a trick on astronomers who thought they were studying the universe.
And she says that we have been studying matter that makes up only a small fraction of the universe. The rest of the universe is stuff that we don't understand and we can't see yet. What makes up you and me and the planets and the center of the galaxy, that's normal matter, that's everyday matter, but that is not the bulk of the matter in the universe. I mean, you're totally flipping the script of what we understand.
It's kind of the equivalent of the realization that the Earth isn't at the center of the universe.
Now, not only is Earth not the center of the universe, now the matter that we knew is not the center of the universe. That most of the matter in the universe is some crazy thing that we can't even describe. We have no idea what it is. It's mind-blowing. It kind of hurts your brain to think about it.
It's almost an anti-Eureka. Vera Rubin didn't discover something. She discovered how much we don't know. A blank in our knowledge. Today, that blank is still there, but it's not stopping scientists from trying to fill it in. I talked to Vox Science reporter Brian Resnick to figure out what scientists have been able to learn about dark matter in the decades since Vera Rubin's research. We started with the most basic question. What's the stuff of it? What is it made of?
Yeah, so no one knows. So if you don't know, if you've been confused, you're where science is at. We don't know what dark matter is.
Do we have any kind of guesses about what kind of thing it is?
Well, scientists think it's a particle.
What's that? Is that like an atom? Smaller than an atom?
Smaller than an atom. So particles are the basic building blocks of nature. They're like the smallest Lego brick that makes up reality. And so we think that dark matter just might be another one of these little Lego bricks.
Okay.
But it's as a building block of nature, it's really, really weird. You couldn't touch dark matter if you tried. It would just go right through your body. It's kind of like a ghost.
Okay, so it's invisible. You can't touch it. It kind of sounds made up.
It's not made up. This is what our observations lead us to think. Astronomers have even seen these galaxy clusters smashed together. And when this happened, the dark matter just went straight through.
Huh.
And that's what makes dark matter really hard to find.
Yeah, how do you find something that is invisible and untouchable? It kind of sounds like an impossible problem.
It's just shy of impossible,
okay,
which is really cool. And, to solve it, we actually have to go to some of the deepest places of the Earth.
My name is Priska Cushman, and I'm a professor of physics at the University of Minnesota.
So I talked to this physicist, Priska, who I have to say, in one of our conversations on video chat, 2 of her pet birds just flew into the shot and one landed on each of her shoulders and she just continued the interview. And
really?
Yeah. I won't call her a pirate, but she's at least this really cool explorer. She's working on this experiment at the bottom of a mine.
You get togged up in a suit with a hard hat and a utility belt, and you get into a large, enormous elevator that takes you down with, of course, all the rest of the miners.
The miners get off before the scientists, and actually, because the mine is so deep below ground, it's actually warm down there because, it's closer to the center of the Earth.
And then you exit into a dusty and hot environment. You're there in a regular mine drift, so you have to walk about 1 kilometer to get to the laboratory itself.
The really hard thing about finding dark matter is that it just passes right through normal matter. And the thing is, most of our all of our scientific equipment is made out of normal matter. So it's like trying to catch a ghost baseball with a normal mitt.
There are billions and trillions of these dark matter particles coming through the Earth, coming through you and me, coming through our detector all the time. But mostly they don't interact with the detector. Mostly they just go right through it because they're so weakly interacting.
But, and this is the hope, every once in a while, a dark matter particle might just nudge a little bit of a nucleus of some atom of normal matter.
So that the crystal within which that nucleus is gives a tiny little shiver that we can actually detect.
So the metaphor here, and this is really simplified, is they've created this extremely subtle bell.
If you push one of the nuclei out of place, it's like giving a little tap on the bell. And that tap is so faint that it is almost impossible to hear when you're listening to all the other taps of all the other particles hitting it.
So that's why they've gone deep underground. This thing is shielded from the cosmic radiation that comes from space, that comes from our sun. And there's just this beautiful patience to it of just kind of waiting and listening and hoping that, the most common source of matter in the universe will make itself apparent to us one day.
And have they found the particle yet?
No.
I really did get into this business because I thought I would be detecting this within 5 years.
And it's been almost 20 years for her, and still nothing.
I guess I'm less sanguine about the possibility that I'll discover it in 5 years.
There are experiments all over the world trying to detect dark matter, and they're even trying to create it at the Large Hadron Collider, the big particle collider in Europe.
Uh-huh.
And no one has found anything.
I gotta say, I get that all these scientists are looking for this all over the world, but what if it's just not out there? It's invisible, it's untouchable. We've been looking for it for decades. What if there's just another way to go here? When I was talking to Ashley, I kept thinking about the choice Vera Rubin had out there in the desert, that there were these two possible explanations for what she saw.
Either Newton's law of gravity is wrong, or we have no clue what's going on at the outer edges of a galaxy.
Astronomers basically chose the second option, right? That there's tons of dark matter out there. It explains why these stars are moving too fast. But we never really tackled that first option, reworking gravity. So, instead of looking for this invisible particle that sounds kind of like a fantasy, what if we just kind of tweaked the laws of gravity?
This is possible.
Really?
It makes a lot of the physicists, particularly the ones I spoke to in learning about this, kind of uncomfortable. They don't want to just throw out all these great observations that they've been making. But at the same time, they know this other door, this idea that, maybe dark matter is something of a mirage created by gravity, something we don't understand about gravity. They know that door isn't closed. And
okay.
I spoke to this other physicist, Priya Natarajan, who just loves thinking about these big picture problems in science. And she told me that the split to either find a physical thing or to rethink our basic assumptions, it's happened before.
In the mid-1800s, we were mapping the orbit of Uranus, which takes a long time to go around the sun, right? And what was found was that the actual shape of the orbit was slightly different from Newton's laws' predictions.
That was a huge problem. Newton's laws, not supposed to be broken.
But Urbain Le Verrier, an applied mathematician from France, realized, there's an interesting possibility, which is that maybe we are missing an observational fact. There is another planet beyond Uranus.
Some source of gravity pulling on it, making this wobble.
And given the wobble, given the departure of Uranus from Newton's laws, he was able to predict exactly where this planet ought to be.
And, lo and behold, scientists found this planet and they called it Neptune. The funny thing is, not too long after that, a similar thing happened.
There was an anomaly in the orbit of Mercury. And Urbain Le Verrier said it's the same explanation. You are missing, perhaps, a planet that lies between the sun and Mercury. And he called it Vulcan.
They searched for Vulcan. I saw this little story in the New York Times from 1876. Please, if you can, look for Vulcan, look for this planet crossing the sun.
But they never found around Vulcan. And that anomaly remained.
It actually turned out like our theory of gravity needed to be updated. Einstein needed to come along. He told us that massive objects like the sun actually bend space around it. And his explanation solved the problem. It explained why Mercury's orbit was where it was.
So we really needed a reconceptualization of gravity.
Huh. So on the one hand, we could just find dark matter like we found Neptune.
Yep.
But it's possible that we just need to update our theory of gravity again, which would mean there's no dark matter, just like there's no Vulcan?
Yeah, there's no such thing as planet Vulcan. And, like we might not ever find the dark matter particle either.
There may not be resolution because inherent to the nature of science is the fact that whatever we know is provisional. And, it is apt to change. So I think this is what, motivates people like me to continue doing science, is the fact that it keeps opening up more and more questions. Nothing is ultimately resolved.
So what does that mean? I mean, is the idea that we can just never know anything about dark matter for sure?
No, I think the lesson is more like knowledge is really hard won. But part of the process of that is trusting our observations. People are looking for dark matter because our observations tell us it's there to find. And there's a lot of evidence that it is there to find.
Like more than stars moving fast on the edge of galaxies?
Yeah, so we definitely see the stars moving fast at the edge of the galaxies. That's a huge piece of evidence. Mm-hmm. But we also see evidence of dark matter in these like kind of bubbles in space, like matter can distort the space around it. And we see light actually bending around dark matter. We can also create these maps of where dark matter is in the universe by looking at where it bends light.
There are these flows of dark matter, and then there are regions where dark matter filaments intersect. That's where gas falls in, cools, forms stars, and you form galaxies.
Dark matter is the scaffolding of our universe. Like, it doesn't just hold galaxies together and keep stars from flinging apart. It's why galaxies are where they are in the first place. When we look into the night sky and we see galaxies, dark matter is the reason why we see what we see.
It would be correct to say that dark matter actually shapes the entire visible universe.
Okay. Let me see if I can put this all together.
Go for it.
Vera Rubin kicked all this off by saying, stars are moving way too fast and we need an explanation.
Yes.
And the basic idea now is that it's dark matter because that could provide all the extra gravity we need.
Yeah, dark matter is that source of mass.
But it's still technically possible that we could just rewrite gravity to explain this all away, kind of pull an Einstein?
I mean, you try pulling an Einstein. Yeah, technically it's possible, but there's a lot more evidence on the side of dark matter.
Right.
We can see the way it bends light. It helps us explain how galaxies formed. And, at the end of the day, yes, we are still missing the key piece of evidence that dark matter is real. We haven't found the particle.
Right.
But that doesn't take away from everything else we know about it.
It's like you're on a beach, you have a lot of sand dunes that kind of form. And so we are in a situation where we are able to understand how these sand dunes form, but we don't actually know what a grain of sand is made of.
Noam, I know you were saying that the dark matter kind of felt made up. Do you still feel that way?
I guess hearing this, I can get behind the idea that we don't actually have to know every tiny detail of a thing in order to understand, how it works and how it affects the universe in all these ways. And I can see why all these scientists are spending so much time looking for something that has the potential to be so important.
Yeah, dark matter is a lot to accept. And you don't have to be perfectly confident in it because, we don't have the perfect evidence.
So, how much do we have to accept? I know there's a lot of dark matter out there, but do we know exactly how much there is?
It's believed there's 5 times the amount of dark matter compared to normal matter in the universe. It's funny even calling it normal matter when most of the matter in the universe, the vast majority of the matter in the universe, is dark matter. And, this whole time we've been talking about dark matter like it's one thing, But it doesn't have to be. Like, there could be this whole kind of ghost universe.
I mean, particle physicists are really playing with this really interesting idea of an entire dark sector, like an entire set of particles that are mirrored with the particles that we know about.
It's like there's this kind of shadow universe that we don't have access to that is made up of different components that kind of exists like as a ghost enveloping our galaxies. We don't know what more, if we keep pulling on this thread of dark matter, what more we'll find behind that veil, in that abyss.
It really just feels like that scene in Men in Black with all the marbles, you know? Or like, imagine like looking up at the stars and feeling so tiny, but, you know, like times a million, like even all those stars out there are insignificant compared to dark matter.
Everything we know, everything we see, everything we've cataloged as being the universe is really only a tiny sliver of the universe. And that's just humbling.
Oh, totally. I mean, I think it gives you intellectual and kind of epistemic humility, right? That we are simultaneously like super insignificant, you know, tiny, tiny speck of the universe. But on the other hand, right, we have like brains in our skulls that are like these tiny gelatinous cantaloupes. And we have figured all of this out. In the grand scheme of the cosmos, you know, we're just like tiny witnesses who are here for a speck. Our lifespans are tiny, not even a wink of the eye, as it were. You know, it's something that should make us all feel really humble as well as be in total awe.
The only thing I can think about is the feeling that makes me feel is, have you ever hiked the Grand Canyon, like to the bottom?
Not all the way to the bottom, no.
So you get to the Grand Canyon, it looks enormous. You're at the rim. It looks like this like oil painting, like it's so huge. But then as you start to descend into it and get towards the bottom, it only starts to look bigger. Like you realize that like little details that you saw at the top are actually huge, like craggy rock faces that descend hundreds and hundreds of feet. And you just feel so small. And I love these moments of like realizing the questions are so profound and so big. You know, there's a sense of optimism in a question, right? Like it makes you feel like we can know the answer to them. We can fill in a little bit more of the whole of our ignorance.
I feel like this is exactly Vera Rubin's story. You know, like she got us here to the edge of this canyon. And honestly, this is the kind of thing that science doesn't always celebrate. I mean, Vera Rubin was sort of overlooked in her lifetime. She never won a Nobel Prize, but really she's the one who got us started on this path.
Yeah, and we don't know what we're going to find down this path. Like this whole rich discussion we've been having about dark matter and what it is and what it could be, it's all because of her. And it's all because she pointed to this big blank spot of what we don't know.
Earlier this year, we finally got a new lead in the hunt for dark matter. It's not the particle itself, but it's something different. A mysterious subatomic wobble that could someday lead us in the direction of dark matter. Or it could help us rewrite our understanding of the universe. That's after the break.
The patience of science parallels the precision of its instruments, reaching into the world of the infinitely small, interpreting it in terms of a new language of
unexplainable.
We're back. I'm Noam Hassenfeld, and this is Unexplainable, a science show about everything we don't know. In the first half of the show, we talked about the discovery of dark matter, this invisible, untouchable substance that holds our universe together. Even though scientists know what it does, they still don't know what it is. They haven't found it. But earlier this year, a lab outside of Chicago came across a potentially tantalizing clue.
Experiments at Fermilab in Batavia, Illinois showed that a certain subatomic particle disobeys the laws of physics as scientists have written them.
Physicists are excited and they say this could be a major breakthrough in our understanding of the universe.
I think it's quite mind-boggling, and they have the potential to turn physics on its head.
I think the whole physics community is in a tizzy.
Jessica Esquivel is a physicist who works at Fermilab in Illinois.
We're very, very close to potentially new particles that exist beyond the standard model.
The standard model. It's one of the most important ideas in physics.
So the standard model is an attempt to catalog all of the building blocks of the universe. And the way I like to kind of explain it is it's sort of like the periodic table.
The periodic table of elements lists all types of atoms in the universe, but even those are made up of other, smaller things.
You have atoms made up of electrons, protons, and neutrons, and for a long time we thought that that was it.
Physicists thought they'd hit the bottom.
And then we dug some more and realized that protons and neutrons are actually made up of more stuff called quarks. They're a building block of the universe.
Physicists found that electrons couldn't be broken into smaller parts either, so they count as building blocks too. And then over time, they started finding some weirder particles outside atoms that also couldn't be broken down.
You have electrons' heavier cousin, the muon, and weird things like neutrinos.
So these are the kinds of particles that make up the standard model, the basic building blocks of the universe that we know of. But physicists are still looking for more. And to do that, they need to find holes in the standard model where new particles could fit.
And we're at a point right now where we might have found a hole.
And it all has to do with the strange wobble of one of these standard model particles called a muon. Now, if you've never heard of a muon, don't worry. Lots of smart people on TV haven't either.
Have you heard of a muon?
No.
Muons are sort of like less stable versions of electrons.
How do you spell it?
M-U-O-N.
And these weirdly wobbling muons could change the future of physics.
That's why it's so exciting. It hints towards something that we haven't seen before.
Open that standard model. Hope it's open that standard model. Open it up. Let me hear it for the muons. Open that standard model. Help us open that standard model. Open it up. Let me hear it for the muons. Wobbling muons. Open that standard model. Help us open that standard model. Open it up. Let me hear it for the muons.
Okay, so Jessica, this muon experiment you worked on at Fermilab might be pointing toward this hole in the standard model. So does that mean the standard model is incomplete?
I mean, we've known for a good minute that it's incomplete. And the reason why we keep poking at it is to try and figure out where the hole is.
Mm-hmm.
One of the big reasons why we know it's incomplete is because we know of this idea of gravity. And there is no particle or force carrier in the standard model that describes this notion of gravity. But we know it exists, right? Because apples fall from trees and I'm not floating off my seat.
Okay, so one gap could be a particle to help explain gravity.
Yes. But then also, when we look at actually everything that's out there, the standard model only consists of 5% of everything.
Mm-hmm.
And the rest of that is dark matter and dark energy. And we still haven't figured out how that falls into our theories and how that falls into our standard model. So there's a whole bunch of questions that we know are there. And there's a whole bunch of things that we know exist, but we haven't been able to kind of fit it into this standard model.
So how exactly does this muon experiment point to a hole in the standard model or a new particle to fill that hole?
So the muon G-2 experiment is actually taking a very precise measurement of this thing that we call the precession frequency.
Okay.
And what that actually means is that we shoot a whole bunch of muons into a very, very precise magnetic field, and we watch them dance.
They dance?
Yeah. When muons go into a magnetic field, they precess or they spin like a spinning top.
Why do muons dance?
So one of the really weird quantum-y sci-fi things that happen is that when you are in a vacuum or an empty space, it actually isn't empty. It's filled with this roiling, bubbling sea of virtual particles that just pop in and out of existence whenever they want, spontaneously. So when we shoot muons into this vacuum, they're not just muons that are going around in our magnet. These virtual particles are popping in and out and kind of changing how the muon wobbles.
Wait, sorry, what exactly are these virtual particles popping in and out?
So virtual particles, I like to see them as kind of like ghosts of actual particles. So, we have photons that kind of pop in and out, and they're just kind of like there, but not really there. And I think a really good kind of depiction of this like weirdness of quantum mechanics is Ant-Man.
The Marvel movie?
So there's this scene where he shrinks down to the quantum realm. And everything is kind of like wibbly wobbling and something's there, but it's really not there. That's kind of like what virtual particles are. It's just kind of hints of particles that we're used to seeing, but they're not actually there. They just kind of pop in and out and just mess with things.
So quantum mechanics says there are these virtual particles, sort of like ghost particles we already know about in the standard model, popping in and out of existence.
Mm-hmm.
And they're bumping into muons, making them wobble?
Yes. But again, theoretical physicists know this, and they've come up with a really good theory of how the muon will change with regards to which particles are popping in and out. So we know specifically how every single one of these particles interacts with each other and within a magnetic field, and they build their theories based on what we already know. So what is in the standard model.
Got it. So even though there are these virtual particles popping in and out, as long as those particles are things we know, like versions of particles in the standard model, then physicists can predict exactly how they're going to make muons wobble.
Mm-hmm.
So did something different happen? Were the predictions off?
So what we just unveiled is that precise measurement doesn't align with the theoretical predictions of how the muons are supposed to wobble in a magnetic field. It wobbled differently.
And the idea is that you have no idea what's making it do that extra wobble, so it might be something that hasn't been discovered yet, something outside the standard model?
Yeah, exactly.
So does this break the standard model? I've seen that in a bunch of headlines.
No, I don't think I would say the standard model is broken. I mean, we've known for a long time that it's missing stuff. So it's not that what's there doesn't work as it's supposed to work. It's just that we're adding more stuff to the standard model, potentially. So just like back in the day when scientists were adding more elements to the periodic table, even back then, they had spots, right, of where they knew an element should go, but they haven't been able to see it yet, or they haven't been able to like create it yet. That's essentially where we're at now, is that we know we have the standard model, but we're missing things. So we have holes that we're trying to fill.
I wanted to get a sense of exactly how physicists are thinking about these new holes in the standard model and how they might try and fill them. So I called up Nosheen Shah.
I am a professor of physics and astronomy at Wayne State University.
Just to be safe, I wanted to make sure this tiny extra wobble on these tiny little muons couldn't just be some sort of mistake. Like maybe they just measured it wrong, or maybe someone spilled coffee on the particle accelerator.
No, we are sure.
Nosheen is pretty sure because the most recent muon experiment matches one that scientists have done before at another particle collider called Brookhaven.
20 years ago, we did this experiment at Brookhaven, and we, set up these muons and made them go around in a magnetic field, and we looked at how much they wobble. And it turned out that they seemed to wobble a tiny bit more than they should.
The results were exciting, but they weren't certain.
You do need to be very careful about, what if there is something that you have not thought about that impacted what the experimental measurement that you did, which is why you always need to validate. So that was the whole reason for setting up the Fermilab muon G-2 experiment.
New experiment, new detectors, new location, all to see if they can still get that extra muon wobble, to make sure the original experiment replicates and that first one wasn't just a coffee spill.
So you hopefully are not going to spill the same coffee in the same place. And the results are very consistent with the ones from Brookhaven. So what we are pretty sure about is that there's no screw up in the experiment.
There are still conversations happening right now about some of the absurdly complicated math here. But Nosheen says that no matter what, something weird is probably happening.
Exactly. Which is why I think that I find this, what's happening right now, like super exciting, right? Because something's going on somewhere, right? And so it's like, all right, we got to hunt to see where it is.
Nosheen highlights 3 explanations for what's causing this extra muon wobble that are worth discussing. First, there's something called a leptoquark, which would be a new particle we haven't seen before. Then there's supersymmetry, which would give us a whole set of new particles. And finally, there's a possibility of an entire new force we haven't discovered yet. So, option 1.
Leptoquarks.
Leptoquarks are particles that would be able to interact with muons and quarks, or even turn a muon into a quark. Physicists have talked about these in theory, but this extra wobble could be a sign that they're real. Or the wobble could be a sign of option 2, supersymmetry.
I really like supersymmetry. It says that for every standard model particle, there needs to be what we call a superpartner associated with it.
It's called supersymmetry because it gives every particle in the standard model a mirror particle that's almost, but not quite the same.
So it's actually an idea that's been there for a long time. And we have been looking for the signs of this type of theory for a while, and we haven't seen anything yet. But I personally still find it one of the most compelling stories.
If these particles were discovered, it would be enormous. It would essentially double the number of particles in our standard model. And these new superpartners already have some pretty great names.
So we decided that we're going to call all the superpartners by putting an S in front of the name. So, for example, the electron must have a selectron, and a muon would have a smuon associated with it.
My favorite is definitely the squark, which would be the supersymmetric partner of the quark.
And we have very serious, very technical seminars and colloquia and discussions with all of these names.
But supersymmetry is more than just funny names.
The nice thing about these supersymmetric models is that they come with a particle which can actually be a dark matter candidate.
So if this muon wobble leads us to supersymmetry, then supersymmetry might lead us to discovering the dark matter particle.
Right.
So that's option 2, an entire set of new particles. Option 3 gets way weirder.
There is a third prong, which is, for example, an additional force.
Not just a new particle or a set of new particles, but an entirely new force. Something like electromagnetism that we haven't discovered yet. And that could be making the muons wobble so much.
So apart from just our electromagnetic and weak and strong force, maybe there is an additional force that we don't know about.
And this new force would also come with its own new particle.
Well, it's coupled together in the sense that usually new forces also come with new force carriers, right? So just like, the electromagnetism, right? That's the electric force that's mediated by a photon, by light, right? An exchange of photon is what mediates the force.
So option 3, this new force, along with its new particle, could be wobbling the muon.
So if you had a new force, then that could be causing some sort of little wiggle there.
Okay, deep breath. We've got these three possibilities to explain the extra muon wobble. It could be caused by a leptoquark, this new particle, supersymmetry, a whole set of new particles, or maybe even a new force we haven't discovered yet. This wobbling muon in the Fermilab experiment, it's like a little breadcrumb of a clue. And we've got these three ideas of what could be making these crumbs. So the next step is for scientists to try to figure out what the whole loaf could be.
What we have to do is figure out the ingredients of this breadcrumb, right? Did it have a little cinnamon on it? Or maybe some vanilla? So you say, okay, this hints to me of a particle which has this type of characteristics. If there existed a particle with these type of characteristics, I should be able to do this experiment and be able to produce it directly.
Essentially, scientists need to keep doing more experiments to try and head down each one of these paths and see if these breadcrumbs lead to a loaf.
We actually do have a whole bunch of different experiments running right now, right? Which are, in fact, looking at, all of these different types of theories in different ways. It's a constant dynamic process.
That constant dynamic process is right on the edge, just peering off into the unknown of new particles, new forces, new physics. Look, do you really need to know what a lepton or a leptoquark is? Probably not. But all of this amounts to the fact that physicists are still trying to figure out what our universe is made of. And the Fermilab experiment might just be pointing in the right direction.
I hope so. I really hope so.
Nosheen isn't the only physicist hoping.
I've been doing particle physics for maybe 15 years, and there's been a bunch of things that have come and gone. And this is really the first thing that's come and stayed. And so, to be honest, I don't even really know how to feel in these situations. We're sort of trained to always be very skeptical. And it's the first time that it's like, oh, how are we going to respond to this thing that is kind of unexpected?
The fact that we're chasing new physics and we're so close we can taste it. It's the unknown.
It's like the first bite of a really good cookie, and you know that the next couple of years we get another bite, and there are so many things we don't understand about the universe.
What's going on with muons? What's going on with supersymmetry?
Where does dark matter fit into all of this?
Why is the universe the way it is?
Why are we the way we are and not some other way?
I think there's something that's really innate in people to want to know about who we are and where we come from and what our place in the world is. And I think that there are a lot of different ways that we can answer that, whether it's through stories or music or film. But I think also through physics that we can actually peer into what's at the heart of our universe. And it's exciting that this might give us a clue as to what is really going on.
And the fact that the work that I'm doing could potentially be in textbooks in the future. People can be learning about the dark matter particle that G-2 had a role in finding. That's it. Like, it gives me chills just thinking about it.
This has been Unexplainable, a science podcast from Vox about everything we don't know. If you like what you heard, please check us out on Apple Podcasts, Spotify, wherever you listen. We've got episodes on fluorescent pink flying squirrels, the constantly changing height of Mount Everest, what could be causing long COVID. There's something for everyone. Thanks to all the physicists who spoke to us for this episode. So that's Jessica and Nosheen, but also Brendan Kieberg, Priska Cushman, Priya Natarajan, Brian Chouvet, Jessica Muir, Sarah Demers, and Rodolfo Capdevila. This episode was produced and reported by Brian Resnick, Noam Hassenfeld, and me, Bird Pinkerton. We had editing from Meredith Hodnott, Amy Drozdowska, and Liz Kelly-Nelson, with extra help from Eliza Barclay, Jillian Weinberger, and Allison Rocky. Our music was written by Noam, and our sound design and mixing came from Christian Ayala and Afim Shapiro. Mandy Nguyen and Cecilia Lay fact-checked this episode. Lauren Katz heads up engagement. Catherine Wells is in charge of explanatory audio. And Liz Kelly Nelson is the VP of Vox Audio. Thanks to Brandon Santos, Lindsay Henning, Jesse Poppy, Katie Mack, Catherine Zurich, Alan Lightman, and David Dworkin. The archival tape in this episode came from David and the American Institute of Physics. Unexplainable is part of the Vox Media Podcast Network. You can find transcripts and articles at vox.com/unexplainable. And please feel free to send any thoughts you have to unexplainable@vox.com. Once again, this has been Unexplainable from Vox and from APM, American Public Media.
Open that standard model. Open it up. Let me hear it for the new one. Open that standard model. Help us open that standard model. Open it up. Let me hear it for the new one. Wobbling nuance. Open that standard model. Help us open that standard model. Open it up. Let me hear it for the new